Ooh, awesome. Hi, everybody, and a special hello to all the brownies. Welcome. Hi, we'll wave. So yeah, I'm Laura Rogers. I'm a researcher here at the Institute of Astronomy, and I'm going to talk to you about dead planets around dead stars, which is a topic that's particularly close to my heart because it's what I do every day. So let's get started. So firstly, we're going to look at the solar system. So hopefully you all know that we are currently in the solar system. We are on planet Earth, and that is the third closest planet to the sun. So on the left, you can see the sun, and then you've got Mercury, Venus, Mercury. Can't do words today. It's too much into the evening. We've got Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and then Neptune. And so before the 1990s, we actually only knew about planets in our own solar system. And so how did we go about observing them? So we wanted to know, well, what are these planets made from? What are they like? And so what we would do was we would do things like measure the earthquake wave speed on something like the Earth. And that's because when an earthquake goes off, your waves will go through at a different speed depending on the density of your material. So you can actually learn about what the Earth, or we've even done this on Mars, what they're made from. You can also send really fun satellites out. So we sent various satellites to all of the different planets in the solar system, and you can do remote observations or even land on the surface, as we've done with Mars. And the other thing you can do is you can measure the size, and you can almost weigh the planets, and then you can work out the bulk density. And that's great. We've learned a lot about planets in the solar system. But from the 1990s, we now know of over 5,000 exoplanets. So these are planets around stars other than our own sun. And so we really want to learn more about those. So what are the planets like? Are they hard? Are they soft? Could we walk on them? Could we not? Would we jump really high? Would we not jump very high? And various things. Could we breathe in their atmosphere? And could we sustain potentially life? So it's a very interesting question to learn what these planets are made from. So what I'm showing here is a plot with a lot of different exoplanets that we've observed. And so we're able to get the size and the mass of these planets. And from this, we can infer what the bulk density is. And so what you can see is, if you look at this axis, if your planets are lying in the top region, they're really big, but they are not particularly heavy. So they're probably quite gaseous, and you probably couldn't walk on the surface. But if you're sort of down this region, these are really heavy, but not particularly large. They're more likely to be solid, hence this attempt at showing you some iron. And so if we look at where things in our solar system are, so the Earth lies down here, and this is where we would call terrestrial planets, so like rocky planets. And up here, this is where Jupiter lies, and these are called gas giants. So great that we can do something rough. We get the mass, we get the radius, we can work out roughly what kind of density these planets are. But I really want to know the like nitty gritty. I want to know what elements make up these planets. What really are these planets made from? So if I could have an ideal scenario, I would take the Earth or an exoplanet, and I would hammer it down really, really hard, and I would get it into dust grains. And then what I would do is I'd put it into something like this, which is a mass spectrometer, and this basically would end up throwing out exactly what this planet is made from. And so if I were to throw the Earth, whack it really, really hard and turn it into dust, I would actually work out that this is what the Earth was made from. So we can see it's got 35% iron, 30% oxygen, it's got silicon, all of these wonderful elements that are super important for us to be alive on the Earth. But sadly, I can't actually go to other planetary systems and take the planets and chop them up. So what we do instead is we actually study dead planets around dead stars. And it's a way that we can actually work out what these planets are made from. So What is a dead star? So you may immediately think about this, some of you. I don't know if you've seen Star Wars brownies, but this is a Star Wars reference. Apologies. So when I'm talking about a dead star, I'm not talking about the Death Star from Star Wars. I'm actually talking about white dwarf stars. So when a star forms, it forms out of a cloud of dust and gas. And for a star similar to our sun, it will follow the trajectory across the top. So it will go through its lifetime, and then when it runs out of fuel, we all get tired, so, when you run out of your fuel, sometimes you explode, and that's sort of what happens with stars. And so it will go into its red giant phase, planetary nebula, and then what happens is it leaves behind the core of the star, and this is what you call a white dwarf. And so if your star is much, much bigger than the sun, so really massive, then it would go through a different stage of evolution. But we're really interested in this top stage of evolution. And so in billions of years, when the sun finishes its energy, when it's decided, hey, I'm also tired, I want to go to sleep, it will eventually turn into a white dwarf. So what you can see here is roughly, if you imagine this is the sun, it would extend up and all the way around the wall. That is the sun, but that is the size of the sun when it becomes a white dwarf. And so it keeps most of its mass, but it packs it into a really small radius. And so white dwarfs are like incredibly dense. And so you would only expect them to have lovely little light elements on the outside. So for example, hydrogen or helium. So if you look at this, so this is a binary system. This is actually showing you the closest white dwarf to the Earth. You might look and say, hey, it's that one, but it's not. It's actually this little blue one right there. And so this is Sirius A and Sirius B, with Sirius B being the white dwarf. So Sirius B is very, very blue, as you could see from that picture, but why? And to answer this, you have to go to the electromagnetic spectrum. And this is basically showing you all of the range of electromagnetic spectra from gamma rays all the way through to radio waves. And so everybody, well, everything, and I guess everybody, has a peak wavelength. So everyone kind of emits at a certain wavelength, and we all emit in the infrared, so it's kind of why we give off heat. And the sun has a peak wavelength at yellow, which is why the sun appears yellow in the sky. But Sirius B and white dwarfs are really hot, and so they have their peak wavelengths more in the blue or even purple. Purple's my favorite color, so we love that. So that is why we would therefore expect these white dwarfs to look blue in the sky. So now, what is a dead planet? So again, you might think back, sorry, another Star Wars reference, to this, where a planet got destroyed by the Death Star. But actually, when I say dead planet, I actually mean that they are being tidally disrupted. And so what happens is you take like a chunk of a planetary body, so like an asteroid or a comet or a fragment of a planet, and you push it towards the white dwarf. I mean, we don't physically push it, but other planets push it towards the white dwarf. And because I said before, the white dwarfs are really, really dense. They're so dense that if something were to come near to it, it would just rip it apart. And with my fantastic animation via PowerPoint, you can see that it would therefore tidally disrupt, it would rip up, and then it would fall onto the white dwarf. So here we've got just an animation which is showing you what I just spoke about. So you've got a body that's being perturbed towards your white dwarf. At some point, it hits this tidal disruption radius and then starts to spread out. And so it then kind of forms like a disk, and we have observed some of these disks as well, which is really exciting. And we're hoping to observe some more with the JWST Space Telescope. So you have this disk of material, and then eventually it then kind of falls onto the white dwarf. We call that accretion, so if I say that, that's what we mean. But essentially, it's being eaten by the white dwarf. And then the metals or the elements sink down over time. And so when I observe a white dwarf, I can actually see these elements in the atmosphere. and I can use that to work out what is this material made from. So just to summarize, why have I got a title of Dead Stars Swallowing Dead Planets? So when I say dead stars, we're talking about white dwarfs. And then that swallow dead planets, these are these tidally disrupted bodies that are therefore accreting onto these white dwarfs. And so these are actually called polluted white dwarfs, which I think is a fantastic name, and I really enjoy saying it, so I will probably keep saying that. Great, so how do we go about observing these really interesting objects? So again, we're going to go back to our electromagnetic spectrum. And so what we do is we split light up. So if I'm observing a white dwarf, we're going to split the light up into its constituent wavelengths. And there are, and to find these kind of, we call them pollution lines, we actually do spectroscopy in the optical and the ultraviolet. So we're really aiming for these regions. And then certain elements, for example, iron or magnesium or silicon, they have these kind of chemical fingerprints. And so what they do is they block some of the light at very particular places. So when I look at a white dwarf, I can know exactly what elements are present. And by the shape and the depth of the lines, it tells me how much of that material is in there. And so what I'm showing here, just quickly, so you can see this is a spectrum. So this is actually Sirius B. Sirius B is not a polluted white dwarf, which obviously makes me sad because it's the closest white dwarf to us. It would be lovely if it was, but it is not. But this is what a kind of normal white dwarf would look like. So you only see these kind of absorption lines from, in this one, you only see hydrogen. And so these lines, these are the fingerprints of hydrogen in a white dwarf. But if you were to actually add metals or the heavy elements into the atmosphere of this white dwarf, then you would see all of these additional lines. And this is what you're seeing here. This is a polluted white dwarf. And so you can see there's extra lines from iron and magnesium. And I can look at this and work out what this planet that has accreted onto this white dwarf or been eaten by this white dwarf is made from. And one of my favorite facts, I think, about polluted white dwarfs is actually that the first polluted white dwarf was observed in 1917. And so what I said earlier is that the first kind of planets were discovered around other stars in the 1990s. But actually, someone discovered planetary material in a white dwarf in 1917. They just didn't know it yet. So actually, I think we should have been given the Nobel Prize because I think we were the first. But anyway, the committee's still debating it. They're not, but we can dream. So here I am showing you a periodic table. And so this is just showing us lots of different elements. And the ones that are highlighted are the elements that we've discovered in the atmospheres of white dwarfs so far. And so we're really interested in piecing together all of these elements to kind of work out exactly what these planetary bodies are made from. So I thought I'd give you a couple of results from some work that we do on these. So we take our big telescopes, and I love using Hubble, which is a fantastic telescope that we really hope is going to keep going, so keep your fingers crossed, and also some telescopes in Chile to observe these white dwarfs. So I take my telescope, I point it at the white dwarfs, and I measure the elements that they have there. And then I have a look. So we all want to find water. Let's be realistic. Water is a great thing. We need water for life. We're 70% water. We drink it, you know, it's perfect. So can we find water in exoplanet systems using polluted white dwarfs? So we measure all of our elements, and then we look at the amount of oxygen that we have. And oxygen is part of water. So oxygen, so water is H2O, so 2 lots of hydrogen, one oxygen. Yes, that's right. Had to double check in my brain then. And so we then assess it. So we're like, okay, what elements have we got? Let's pretend to make a rock. So we put all of these elements together, and we form a rock in our heads, and we say, is there any excess oxygen? And so if you have excess oxygen, actually the only way that you could have had excess oxygen is if the body that accreted had water in it. And if you don't find any excess oxygen, great, you've got a lovely rock. You've got a wonderful rock that kind of makes sense, everything's perfect. And actually, we have discovered quite a few water-rich bodies. So we have, I think, about 10 white dwarfs that seem to be swallowing material that was rich in water. So it's really exciting. We're already finding that there is water in other planetary systems out there, and it complements techniques like assessing the atmospheres of whole exoplanets, because these ones are disrupted. So it's a very complementary technique. So we've learned most of the objects seem to be dry, but we do have some that are water rich, which is very exciting. So then another thing that we can assess is actually more to do with the interior structure of planetary bodies. And so there's this thing called differentiation, which basically means if you take a rock and you heat it up, all of your, we call them like iron-loving elements, are going to migrate down to the core. They're really heavy. And so you end up having this dense core that's mostly iron, and then you have a mantle and a crust layer. And so in the core, you're going to be having like as I said, like a iron-rich party with, you're going to have your iron, maybe some nickel, maybe some chromium. And in your mantle, you're going to be having a party with magnesium and silicon and calcium, these different kinds of elements. And so when you're studying these planetary bodies, you can actually learn about the cores and the mantles of these bodies because you know which elements like to have parties together. So the Earth is actually differentiated. So it has a core in the inner region, and it's got a mantle, and it's got a crust. So we know that differentiation happens in our system, but we have no idea whether this geological process happens anywhere else. So how do we go about studying this with white dwarfs? Well, our objects heat up, they differentiate, and then they end up colliding. So systems can be very chaotic, they all whack into each other, and they make these fragments. And you end up having fragments that might be mostly mantle, or mostly core, or even mostly crust material. And then these then get swallowed by our white dwarfs. And then someone like me comes along and says, I'm going to observe it, what do I see? And my most recent paper actually found evidence of a mantle-rich fragment and a core-rich fragment. So it's really exciting, and what we can find is that actually we are finding evidence of differentiation in exoplanetary systems. So it's really quite an exciting thing. So yeah, so I just said here that we've already observed fragments of cores, fragments of mantles, and even fragments of crusts. So I hope that I've convinced you that studying dead planets around dead stars is a great thing to be doing, and hopefully you're convinced it's my day job. So, and we've already characterized over 100 white dwarfs that are eating planetary material. And so we found some that are eating material that seems to be quite rich in water. We found others that are eating chunks of core or mantle or crust material. But actually, most of them seem to be accreting dry material that's very similar to the Earth. So actually, what we're learning is Earth-like material does seem to be commonplace in the galaxy. And so maybe there's a lot more Earths out there, who knows? But yeah, thank you so much for listening. And yeah, happy to take any questions.
Okay, so is this working? It is working. Okay, we have the most fun question tool ever, which is this very squishy fun box we can throw around. So yeah, thank you so much. Does anyone have any question for Dr. Rogers? How's your catching? Hopefully better than my throwing. Here goes.
Good job.
So yeah, so talk sort of straight into the black bit. There you go.
How far away are the white dwarfs?
They're quite far away. So if you look in the night sky, it's actually really difficult to see white dwarfs with your eyes. But that's because they're not only quite far away, but they're also really faint. So they're difficult to see. but they're closer. So they are in the galaxy, they're in the local area, but we can't see any that are not in the Milky Way. So.
There's one
Behind you.
Just pass it behind you.
Oh, I wanted to throw.
How far away is the closest white dwarf?
How far away is Sirius? That's a good question. I wouldn't know in a unit that would make sense. So I don't know if anyone knows in a unit that makes sense. Do you know?
Google might know.
Go. We're gonna Google it. Because otherwise I have to do conversions in my head.
Okay, do you want me to say?
Yeah.
Okay, so when we measure the distance to stars, they're so far away, we have to measure the distance in terms of the speed of light, which I don't know if you've heard of the speed of light. It's the fastest speed there is. We use a unit of distance called a light year, which is how far light goes in 1 year. So you get a new rocket ship, and you set the engine to go at the speed of light. And that's so fast, you get to the moon in 1 second. And then you keep going for a whole year, and you travel 1 light year. So Sirius is about 8 light years away. So 8 years at the speed of light.
Thank you. Where's it being thrown? Hello.
Roughly about how long does it take for a star to go into a dwarf?
A very, very, very long time. So the sun will go into a white dwarf in like 8 billion years. So much, much longer than the age of you or even your grandma. But yeah, billions and billions of years. These are all fantastic questions, may I say.
How many planets are there?
Well, that is a fantastic question. So we actually think that there are more planets in the universe than there are grains of sand on the Earth. So if you've been to a beach, you've seen that there's lots of sand. There's way more planets than there are pieces of sand. But we only know of like 5,000 so far. But that's still quite a lot, because it takes quite a while to count up to 5,000. Maybe you could do that tomorrow in class. I'm sure your teachers would love it. But a lot.
How
many stars are there? Again, fantastic question. Loads. So we think that there might be less stars than there are planets. So we think that there are a lot of stars, billions and billions, across the whole of the universe. But we think that there are more planets compared to stars, because there tends to be more planets around a star than there are stars.
Okay, there was a question. Should we do a I love you got so many questions. Should we give someone else a chance and then go back to the brownies? Is that okay? This young man had a question at the front as well.
How did Earth get oxygen?
Oh, that is a fantastic question. So there was someone who spoke last week who was an absolute expert on oxygen. And so when stars and planets form, they form out of kind of gas and dust, and there's already some oxygen in there. And then, so when it's forming, it will already have some oxygen. But actually, things like plants, they produce oxygen. And so the reason that we have lots of oxygen is because we have lots of plants and various things that give oxygen back. But that is a fantastic question.
So there was a question around at the front. We can go back to the brownies. Just wanted to give everyone a chance. Go on. There you go.
How long does a white dwarf eat a dead planet?
You know, if I knew that, I think I would be a lot richer. So, I mean, I don't know how to answer that well, because I really don't know. We think that it happens fairly quickly. So it gets eaten over time, and then it kind of sinks out. But we think that then it starts to eat more. We think that it doesn't like to just eat one, it likes to eat multiple. But if you know the answer, let me know. We can write a paper together. Yeah?
Take sun to turn to a wife.
Was that how many years until the sun? Yeah, about 8 billion, I think, is the quite a while. Billions and billions of years. We don't have to worry about it just yet.
I know that the is made.
Oh.
I know that the Earth is made up of the 6 elements that humans are made up of, but does the same apply for white dwarf stars?
That is a great question. So stars are made up from slightly different elements to humans. So there are definitely some differences. So remind me of your question. Sorry, I couldn't quite hear. I'm just checking.
I know that the Earth is made out of the 6 elements that we're made out of, but does the same apply for a white dwarf star?
Yeah. So when we think about how planets form in a system, stuff that's really close to a star. So if we think about planets, things that are close in, they actually don't have certain elements. So like Mercury, which is really close to the sun, it doesn't actually really have things like carbon and oxygen because it's too close and it's too hot. So it just kind of evaporates them all away. And then the further out you get, so something like Uranus and Neptune, they will have lots of carbon and oxygen. And so actually white dwarfs and stars in general tend to have a similar composition to the stuff that's further out in a system. So a star would be more similar to something like Uranus and Neptune compared to something like the Earth.
Do you have to say a couple more?
Yeah. If everyone else is happy to.
Well,
you're not eager to get observing, so I totally understand.
Well, they're normally ready for about 9:45 to. So if we do, let's say 3 more questions, and then we'll go into Stargaze.
Yeah, and I can hang outside here for a little bit as well.
Yeah.
So.
Tell you what, should we do 1 more from the brownies and a couple from this side? I think this side of the room has another chance. Is that okay?
Yeah, that's fine.
How far away is the biggest white dwarf star?
How far away is the biggest one? Oh, I mean, I'll tell you a fun fact, which is that when we think about white dwarfs, they're actually really, really weird. Which is if you were to put more mass in, so if you were to put more stuff into a white dwarf and you were to try and make it bigger, you would actually make it smaller. And so the more mass that you have in a white dwarf, the smaller it is. Therefore there's a limit to the size and the mass and the heaviness that you can have a white dwarf. And so most white dwarfs, so even Sirius B, will be quite close to that mass. So maybe 8 light years is the best answer there.
Okay, there's a question here.
So is there a point where polluted white dwarfs, they're absorbing, so say over billions of years, that their chemical composition is changing so much? Will they always be polluted white dwarfs, or are they taking on so much that you forecast they will become something else?
Yeah, that's a really good question. So, woo! What I mentioned a bit earlier on in the talk is that white dwarfs are really, really dense. And so you have this kind of surface layer of gas. And so when you're swallowing exoplanetary material, you're putting stuff in there, but it actually sinks out. So I like imagining it like when you're throwing stones into a lake or something. I don't know if anyone else does that or just me, but you actually watch it sink over time, and eventually you won't be able to see the stone anymore. And that's what happens with polluted white dwarfs. And so the stuff that you're seeing in the atmosphere of the white dwarf has to be accreting right now, because otherwise it would just sink away, and we cannot see it once it's in the middle.
Let's do one more brownie question. Okay, one more question from the brownies. This is the last question.
How many are there?
What was that? How many?
Dwarf planets are there?
How many dwarf planets or white dwarfs?
White
White
dwarfs, I think.
How many white dwarfs are there? That is a fantastic question. So far, we know of about 359,000. So, and hopefully we'll keep discovering more, because actually most stars in our galaxy will end up as white dwarfs. I think 97% of stars in our galaxy will end up as white dwarfs. So they're very, very common.
Amazing. Well, thank you so much, Laura. That was absolutely fascinating stuff. Big hand. Okay, so the plan now is for stargazing. I will lead you outside. So just to let you know what you're going to be expecting, there will be some sort of telescopes and hopefully a bit of a show on the lawn, as well as some telescopes in domes open for you. Make sure you visit. There's a telescope staffed by some undergraduate students to the right through the trees. I'll point it out once we're out there, but make sure you visit it because they get a bit lonely. Okay, do you mind if I just sort of leave you?